Good morning, everyone. As Diane said, my name is Numerical from the University of Witwatersrand, and I'm with Prof. Francisco Ortegòn Gallego in Morocco, and he was here in February to visit us, which we enjoyed very much. So I'm going to read a short biography of Prof. Francisco. Prof. Francisco Ortegòn Gallego obtained his PhD in mathematics from the Universitat de Sevilla, Spain in 1988, and from the Université Pierre at Marie Curie, Paris, 6 in France in 1989. During the period 1987 to 1997, he worked at the Universitat de Sevilla, and since 1997 is working at the Universitat de Cadiz. The research topics that have most interested him deal with problems of mathematical physics and engineering governed by nonlinear systems of PDEs, from theoretical aspects to the numerical simulation. In particular, Julian's modeling, nonlinear elliptic and parabolic equations, similar coefficient, the Aristotle problem, steel heat treating, etc. He has authored or co-authored about 40 articles in impact journals and has participated in more than 60 international conferences as an invited speaker on several occasions or as a chair of the organization. Thank you very much. I hope you enjoyed the talk. Over to you, Prof.
Okay, good morning. Thank you very much, Melo, for these nice words. I feel very honored to be among you, and I hope you enjoy this conference. Okay, so as you can see, this is a collaboration work with a colleague, Amal El-Kush. She is a PhD student at the Faculty of Sciences, University of Abdel Malek Zahari in Morocco. This is the summary of my talk here. So I'll talk about some goals. I'll try to explain what is a PTC, what I mean by a PTC. Some words about solar radiation, the mathematical modeling, some words about the heat transfer fluid, numerical scheme, numerical simulation, and some conclusions. So the presentation deals with solar thermal techniques arising in renewable energy technologies. So the goals are to describe what is a PTC, to develop a mathematical model for the PTC heating processes, to describe a numerical scheme for the resolution of these systems, and to present some numerical simulations. So here is a picture, a nice picture, in order to give you an idea of what we are going to do. So solar thermal techniques are based in the idea of capturing solar radiation incident in a large surface in order to concentrate it on a smaller one. So every one of us has played around with a magnifying glass. What we want to do is something like this, but in a very big scale. Here is a nice quotation due to Jacobson and others back in 2015. They said, solar research is driven by a growing awareness of the issue of climate change. As solar technologies represent key solution for a 100% carbon neutral future. Solar thermal techniques is a branch of the renewable energy technologies. It concentrates solar energy to generate steam that powers a turbine. Different types of solar collector are used in the industry, among them parabolic trough. So what is a parabolic trough? Here is already a picture that you can see what is a parabolic trough collector. So what are we talking about? We are talking about something that it is an enormous, a huge facility. You can see here three guys here, just in the middle of the picture. You can see how big this facility is. So in order to build something like this, you have to put a large amount of money. What is expected is that you can retrieve some amount of that money that you have just put in. So here, in this picture, corresponds to a solar energy generating system in California Mojave Desert. This is the second largest solar thermal energy generating facility. So you have 354 megawatts. The first one is, you can find it in California too, but near the boundary with the state of Nevada. So a parabolic trough surface has a surface of mirrors with a parabolic profile that concentrates solar radiation in a receiver tube here. This is this receiver tube located at the focal point of the parabola. A heat transfer fluid, HTC, flows inside the receiver tube and is heated up by the sun. The HTC is then pumped through heat exchangers in order to generate steam, which is thus used to produce electricity in a conventional turbine. So here are the elements that participate in this device. So we have a reflector, a parabolic reflector. We have the tube. The tube itself is constituted by a pipe, by absorber pipes, and a glass tube. Okay, so the idea is that the solar thermal energy will be transformed into mechanical energy and then to electricity energy if necessary. So I'd like to show you here a nice piece of engineering work. This is the glass envelope and the absorber pipe. So in the middle, just inside, we have the tube, which is made of stainless steel. And then it is surrounded by a glass envelope. And at both ends, we found some elements which are very necessary in order to take into account the different physical properties of glass and steel. So we have first here the glass metal welding, and then in order to make up for the volume expansions of the steel, we need to put bellows at both ends at every single part of this set of glass envelope and absorber pipe. So here is something which is very interesting, that the glass cover is transparent to the radiation of short wavelength coming from the sun, but at the same time are opaque to the radiation of long wavelengths emitted by the absorber tube. So the heat transfer fluid, which is inside the tube, the pipe, the steel pipe, this heat transfer fluid is an industrial synthetic oil. So there are companies, normally private companies, that develop this oil, this synthetic oil. They obviously they kept the formula for themselves. They do not. They kept secretly this formula, but on the other hand, what they provide to the public, to the general public, or even you can find it in the internet, is a leaflet, a technical report with where every physical property, like density, specific heat, etc., as a function of the temperature, is tabulated. So this information is provided by the manufacturer, but the company do not tell you what is the formula of this synthetic oil. So some words about the radiations. Okay, this is the obviously this is the main source of heating of our set. So what we know is we have estimated the power arriving to the outer atmosphere is about 1,367 watts per square meter. This is just the outer atmosphere. But since we already know that our atmosphere is stratified, it is compounded by several layers with different molecules and elements like upper dust, water vapor, etc. So this quantity, this power will be damped down, so that some amount of this power will be absorbed, lost, some amount will be scattered to space, and then so the direct radiation on the Earth, what we can take advantage of is about it is in the interval 33% up to 83%. So this amount will depend on the site you are measuring this. It will depend on the latitude, on the longitude, on the altitude, and obviously it will depend also on the time, on the hour that you are measuring that quantity. It will change during the daylight. It will change this amount. That is obvious. So here is a PTC cross section. Some elements that we will need to take into account in order to derive a mathematical modeling. So I have represented here the different elements that are source terms in our equations. There are source terms due to radiations and some source terms due to convection, and a source term due to the molecular diffusion. Okay, so now what we need to do. Okay, so in the mathematical modeling, we just take into account the thermodynamic balance for the temperature on the glass, for the temperature on the absorber pipe, and for the temperature of the heat transfer fluid. So our known are TG, TAB, and GF. And what we need to do now is just to express these source terms in terms of the radiation, the direct radiations, and in terms of the unknowns. Okay, so to do so, we need to consider many physical properties of the element that that participates in this device. The first one, and the QG, is proportional. Obviously, it's proportional to the direct radiation term, and which involves many expressions that must be taken into account, must be computed. These functions, like the incidence angle, linkage, turbidity factor, air mass, Rayleigh's optical thickness, and so on, they are time dependent. So it depends on the hour, measured in seconds, of the day. And so this must be computed depending not only on the time, but obviously it depends on the site, on the terrestrial coordinates you are measuring these quantities. Okay, so now for the glass cover, we have to for the energy from the absorber, for the glass cover, we have to take into account two different situations. So if we have no pressure, if the pressure is negligible, in the annular space between the glass cover and the pipe, then we use this formula. And but when this space is filled in with gas, for instance, air, then we use this relation, this correlation, due to Rayleigh and Hollands. Okay? This is natural. This is a correlation for natural convection in an annular space between horizontal concentric cylinders. Here there is a function Kf. So this is proportional to the difference of this temperature. And this coefficient here is the effective thermal conductivity, which is an expression which is non-linear of Tg and TAB. Okay, so for the radiation heat transfer rate, we use just Stefan Boltzmann law based on the geometry, emissivity, and temperature of the glass cover or the absorber. So we found here the usual difference of the temperature to the power 4th, given by the Stefan Boltzmann's law. Okay, now for the heat transfer from the glass cover to the environment, this convection term represents the largest cause of heat loss, especially in the presence of wind. This can be estimated from a correlation due to Zhukauskas back in 1972. He proposed these correlations where the Reynolds number and Prandtl number participate in these expressions. Okay, depending on the Reynolds number, we have to take different values of the coefficient C, this value of n. Okay, so for the external radiation heat transfer, then in this case, we also use the Stefan Boltzmann's expression. But here we are taking into account the temperature on the glass and the temperature of the sky temperature, T sky. So T sky is evaluated from a correlation proposed by Swinbank, which gives this expression, where T8 in its turn, Ta is the ambient temperature. These TAs must be also tabulated from the value of the maximum and minimum temperature along the day of the year we are considering. Okay, so for the solar energy absorbed radiometallic pipe, okay, so we have another formula which is proportional to the direct radiation. Again, but here we have some coefficients which are depending on the physical property of the steel, of the material that is made the pipe. Okay. Now the convection heat transfer from the absorber to the HTF, the unit length, we use the Newton's law of cooling. So this source term is proportional to the difference of the temperature between the absorber and the fluid. And we have here this number, which is Nusselt number, which in its turn is a nonlinear function of TF and TAB. We have taken this expression, which is a really almost a brand new formula that we used. We saw it in a paper which has been recently published in 2019, and by using this formula, we obtain some numerical results that were reasonable, and we were very happy with by using this formula. Okay, So here is the set of equations. Once you put the expression we have developed, we obtain this set of three equations, three parabolic equations with boundary conditions and initial conditions. Okay, so we have, this is the mathematical modeling then. Okay, so some words about the HTF using our numerical simulation is we have used Therminol VP-1. So Therminol VP-1, why we have used this HTF? And okay, so we consider a first paper with where the numerical simulation were made by using this HTF, this fluid, so that in fact we would like to compare our result with the one that the paper has shown. That paper had shown. So that on the other hand, the manufacturer of this synthetic oil has a technical report, a very detailed technical report with we have tabulated every physical property, so that we can derive some mathematical formula for the density, for the specific heat, and so on. So evidently, this synthetic oil has temperature-dependent physical properties. So density, specific heat, thermal conductivity, and so on. All everything depends on the temperature. So what we have done is to develop from the technical report. We have developed some formulas, some mathematical expressions for these physical quantities. Okay, so we have done this by the least square method. And we have done this for every physical property. So this is the thermal conductivity, then we reduce Prandtl number, and so on. So here, the blue dots here represent the data provided by the manufacturer, and the solid red line is the formula that we have developed by, as I said, the least square method. Okay, so now we go back to the mathematical modeling. And we, as a mathematician, I prefer to use my knowns U, V, and W instead of TG, TAB, and TF, which is a bit cumbersome. So my model writes like this. And this is a set, as I said before, a set of three parabolic equations in 1D dimension. And with some Neumann and Dirichlet boundary conditions and some initial conditions. So we want to integrate these equations along an interval of time t initial and t final, so that t initial will be close to the sunrise, and t final will be close to sunset. And obviously, we are integrating this equation in space all along the full length pipe. Okay, so in order to obtain some numerical results, what we have done is to derive a predictor corrector scheme with respect to time, with respect to the semi-discretization in time. As a predictor scheme, we have used a semi-implicit Euler method, and as a corrector scheme, we have used a semi-implicit Graham-Nicholson method. This is quite convenient because the combination of this predictor-corrector scheme has given us a scheme with some very interesting stability properties. You have to take into account that we have made 4,000 iterations in time. In fact, we have, for the predictor, we have to solve three times a 1D equations. For the corrector, for the same three times a 1D elliptic problem. So at every iteration of time, we have to solve six times a 1D problem, 1D elliptic problem. Okay, so this is the description of my numerical scheme. So as usual in the finite difference method, we take a partition, not necessarily equally distributed. And so we begin with the first one. Then at the stage 2 is this prediction by using the semi-implicit Euler method. We compute this U bar, V bar, and W bar at iteration n+1 like this. So first we compute U bar like this, then V bar, and then W bar. And here we are using the already computed U bar. And in the equation for W bar, we are using V bar. So the integration, the computation of UN, Vn, and Wn bar is sequential. And then in the correction stage, what we do is to apply a Grant-Nicholson scheme in this way. So the first thing is to compute UN, the new iteration UN at UN+1, I mean, by this. Okay, so then we compute Vn+1 like this, and finally we compute Wn+1 like this. Okay, so this is the flow chart corresponding to the computation of every iteration. So we begin with the initialization. Then if UN, Vn, and Wn has been already computed, then we compute sequentially these intermediate values. And then when we already have computed all these values, then we may compute in a parallel version, in a parallel computation, these quantities, and then we ask if we have already gained the maximum value. So if we haven't reached the maximum value, then we increase by 1 the value of the iteration, and we go and we repeat the process until we have arrived to the maximum value of the number of iterations. Okay, then what we have here is a 1D elliptic problem, and this one in the elliptic problem has been solved by using the finite element method. We have, in fact, we have used just to compare the results, we have obtained 1 order and 2 order approximations. So we use polynomial of degree 1 and polynomials of degree 2, and so that to compare the results. Eventually, what we have realized is that it is not worthwhile to use L2 in this setting, because the result that we obtain, that one obtained with L1 or L2, differs just by less than a half a degree all along the computation. And this, we can, in fact, we can afford an error of 1/2 degree in our computation, because we are talking about obtaining values of the temperature of about 160 degrees and so on. So what we have done is to implement this numerical algorithm by using the FreeFrame++ package. This is distributed, freely distributed. You can download it from the web page, and it is a very powerful, tool in order to solve partial differential equations in 1D, 2D, or 3D. So the procedure begins by initializing the necessary variables in order to solve the full system. Then there are 4 kinds of variables named. The first thing to do is to provide terrestrial and date variables. Then the temperature data for the specified location. Then the physical properties of the mirror, glass envelope, the absorber pi, and the STF. And then the parameters related to the numerical scheme. So, what we have done is just consider the site of Tetuan, the town of Tetuan in Morocco. So we provide the location, so the latitude, the longitude, and the altitude to our software, to our program. We must say that what is the time zone for this site, for this specific site. So Tetuan is +1, so is greenish +1. So I think that Johannesburg is +2. Then we must provide a specific date in order to make our computations. And we need also to specify what is the solar tracking system you are using in this setting. So we have used what we call east-west polar. So in this, you must provide some information about how are you tracking the sunbeams all along the day. And this is one possibility to do this east-west polar. Okay, I have no much time to give details about this. Okay, so from terrestrial and location data, we first compute the true solar time. So this function is computed from all this data and using astronomical formulas. These functions, as I said, has been computing on a Julian day basis, and so it is computed by the second. Then the ambient temperature is evaluated. This is the formula we have used in order to evaluate the ambient temperature along the day. Okay, so we must provide this function Tmax and Tmin from the specific site. So in the case of Tetuan, what we have only is this green dot points, these values, this green, what you have is only 12 values for all the year long. But we need to provide a formula for every day. So what we have done is to use again the least square method in order to develop a formula for the temperature, for the maxima temperatures and the minima temperature. So this is what we have obtained. And for the specific sites of Tetuan, the values of these coefficients, C and G, are this. So we provide this value to our program for the specific site of Tetuan. Then we have a long list of values, of physical values for the discretion of the material that we are using in our device. And so the glass, the pipe, then the stain, the stainless steel, and so on. Okay. Now the parameters coming from the numerical scheme. So we use here, as I said, an implicit Euler Cram-Nicholson scheme. So we have taken as the initial time value sunrise hour, which has to be computed every day, plus 15 minutes. And then as a final time, the final value instant of time is sunset plus 6 minutes. And then we have taken 4,000 points in our discretization. We have used a uniform, in this case, for time discretization, we have used a uniform partition. And as long as the 1D finite element method is concerned for the space discretization, we have used, as I said, polynomial of degree 1 or polynomial of degree 2. And the partition here, we have used a Chebyshev distribution. Okay, so that these points are more concentrated and at the boundary than at the middle, like in the middle of the interval. As initial conditions, we have taken a G-mean and this average values for W0 for the temperature of the transfer fluid. And we have used as the inlet temperature this same value. Okay. Now we have obtained these results. So at the specific site of Tetuan at the specific date, okay, we are assuming at every computation in any day of the year, which is in fact not true, but we are considering that we have a clear day sky. Okay, so there is no clouds in this case. So and we have made this computation. If the day is cloudy, then we have to the computation must be redone so that there is a reduction of the direct radiation arriving to a specific location. So as you can see here, we are representing here the outlet temperature evolution. So these are the maximum temperature we have obtained in our computations. So in red, the red solid line is the temperature on the absorber, then the fluid, and the blue one is correspond to the glass. So to different dates, we obtain obviously different evolution of the temperature. Okay. So here is also in June and in December, there is something that shocked us when we first made our computations, and is the thing is the temperature you obtain in June and the temperature you obtain in December, the maximum temperature are almost the same. And this was a surprise for me, because I thought that in June must be, since the ambient temperature is hotter, then the temperature should be greater than the one you obtain in December. But that's not the case, because there are some effects that intervene also in the expression of the radiation arriving to our device. And so that was the reason. So obviously in June, this day, this is a solstice day. This one and this one are solstice days. And so the big difference between June and December is the sunset and sunrise interval is greater, much greater than the one corresponding to December 21st, obviously. The maximum temperature we obtain is in the equinoxes dates, so in September 21st and in March 21st. Okay, so this is a comparison of this temperature. We have represented here the outlet temperature of the fluid for 6 different dates, and here, so you may compare here the different temperature that you obtain depending on the date. And here we have represented the temperature all along the full length pipe. So what we see here is a almost linear behavior of this temperature. Okay. So another aspect that you must take into account is the efficiency of your device. So we measure this efficiency as the fraction between the power obtained by the PTC and the power arriving in the PTC from the sunbeams. So we measure this quantity all along in one day. We have compared here what is happening at this equinox date and this solstice date in order to measure this efficiency, to compare this efficiency. And so we obtain an efficiency between the sun, a value greater than 60% and a value a bit greater than 80%, which is not so bad. So as a conclusions, I must say that renewable energy has been a standing trending topic from the last decades and has attracted the attention of many public and private companies worldwide. The decision of building a solar parabolic trough plant in specific location must be supported by the quality of the future performance of this facility on an annual basis. In this regard, mathematical modeling and numerical simulation has shown to be powerful tools in order to predict the performance and efficiency of a solar thermal parabolic trough plant. We have fully detailed a mathematical model for the description of the temperature, Gg, dAB, and Gf in the 3 different elements of PTC, namely the glass envelope, the absorber pi, and the heat transfer fluid. The numerical algorithms combine the finite difference method with the finite element method. This predictor corrector scheme has shown good stability properties after 4,000 time iterations. The numerical results show an evident dependence on the PTC performance and efficiency on the day of the year. There is similar behavior in the solstices days or the equinoxes days with respect to the maximum temperature risk by the HGF. And so here is some bibliography. I let you here. This is the paper we have already published, my colleague Amal, myself. So it is I am detailing here the DOI, the DOI, so that you can download it because it is an open access paper. So you have every detail of what I have already tell you about. It is here. You may find every detail in this paper. And there are some papers we have studied in order to develop our formulas and to study the problem. So thank you very much for your attention.
thank you very much for the wonderful presentation.
Okay, thank you.
I want to ask if there's anyone who would like to ask a question either via the chat or they'd like to unmute themselves and ask a question.
In any case, when I gave my talk in Johannesburg 3 weeks ago, someone just told me that it may be interesting to build up a site like this in Johannesburg. And this may be very, very interesting too, of course. The thing is that in Johannesburg is 1,700 altitude. And this is very nice because the sunbeam has to run across a distance, a lower distance than a site that you put at 300 or 200 meters from the level, from the sea level. Yeah. Okay, it is true that maybe in Johannesburg the weather is cloudy, is mainly cloudy or not, or just in winter. Excuse me, in summer. During summertime is rather cloudy, but during winter time is almost a clear sky. Is that true?
Well, I guess with climate change, I can't tell, but I think usually around December and January, that's when we have the most rain in Johannesburg. But other times of the year, we have clear skies, clear blue skies.